Hello everyone, welcome to my channel Precision Manufacturing System. I'm coming back with a new project which is related to cyclic hardening and cyclic loading. This example is a CE tutorial, and I'm going to explain about notched beam with cyclic hardening and cyclic loading. In this example, I'm trying to explain about notched beam with 2D planar shell deformable, and I would like to explain about cyclic hardening, material property, explain about partition, cyclic loading, and also I would like to explain about bias in the seat size, seat age in mesh module, and also I explain how to draw a stress strain curve using operate on XY data. In this example, as I consider plane strain example notched beam base because of the existing symmetric in loading boundary condition and the shape. We just consider half of our notched beam. I have already drawn my plane strain notched beam, so I just show the dimension of my beam in a sketch module using feature edit. As you can see, this is the dimension of my plane strain notched beam. I use millimeter measurement, so you can see my part notched beam. As you can see in here, I consider fillet here and as a notch, and you can see all of the dimension we need for drawing our beam as a plane strain beam. So please considering this dimension for drawing your beam. After that, after drawing the beam in a sketch model, we try to define material properties. So before doing anything, please consider your notched beam as a 2D deformable and shell model. For example, you can see here 2D deformable shell, and consider approximate size. For example, our maximum value is 52, so we can consider, for example, 100 here. So before I have drawn my notched beam, so I eliminate, cancel this section, and just try to draw your plane strain beam, and then we continue our example with defining material property. For material property, we consider this property mat as a name of our material property, and consider elasticity, mechanical elasticity, elastic, and define Young's modulus, and also position ratio as a elasticity of our material properties. So we consider 200,000 as a Young's modulus, and Poisson ratio as a 0.3, and also we consider material plasticity, mechanical plasticity, plastic, and define our plasticity property. In hardening, please consider combine and for data type, please consider parameter, and consider this property for our plasticity. Yield stress at zero plastic strain, please consider 200, and kinematic hard parameter C1, please consider 225 and 500, and for gamma please consider 81. To define your material property, plasticity of your material property, and also click sub optional and consider cyclic hardening, and define your equivalent stress, and please consider use parameter, and equivalent stress consider 200, Q infinity consider 2000, and hardening parameter please consider 0.226. After that please consider OK and OK. So at this time we define a section for our beam. So click create section, and solid homogeneous, continue, material must be matte, okay, and consider, and then assign your material property on your notched beam, okay, and click and okay, section 2, and okay. So we assign our material property on our notched beam. After this module we refer to assembly module and import our part in assembly module. It's necessary to import your part even if you have just one part. Is necessary to import your part in your assembly module. So we consider independent mesh on instance and okay. So we import our part, just one part in our assembly module. The next module is a step module, and in this step we try to define define our step. So we need to define two step. Create step 1 name is loading. And we consider static general step. Continue. Time period in this step is 1, and incrementation please modify based on my modification, and consider 0.125 as initial, and minimum must be is okay, and maximum must be 0.25, and it's not necessary to change anything in other tab, and it's okay. Okay, another step is additional loading and unloading. Additional loading and unloading, and also for this step also consider a static general type, and continue. Consider time period 6, and also modify incrementation based on my modification, and it's okay. And also this one is 1, and this one is 0.125, and okay, and then okay, please go back in assembly module and do partition in your model for considering boundary condition and loading point. So we use go to use tools and partition, and use face tab and sketch, and so your model goes back to a sketch module to draw your partition. So it's just necessary to draw some line like me. Please doing what I'm trying to draw for this section. Okay, consider for example 10 here, 10 here, 6 here, and another line must be here. I'm trying to do partition our beam because we want to modify seat size, because some of the parts, some of the section in our beam, for example in here, is more important for us than here, so we need a smaller seat size than here to decrease our computational time. In this example, it's computational time is not too significant, but I'm trying to do partition. Just want to teach you how to define partition, and also how to use seed edge and bias in your model. So another line must be here. Okay, please consider example 3. Another line, for example, in here. Dimension 4, and this one. Okay, this is our partition. Please just consider this partition on your model. If you want to modify your partition, you can consider another method or another section to modify your model, and use accurate seed size in your model to get more accurate result. So after drawing the line, all of the line, please click on down. Okay, the sketch is over defined, so we need to delete this section, this dimension, and then okay, done. You can see the partition in your model. Okay, we define a step module, and for interaction it's not necessary to go this module, because we have just one part and there is no any interaction between part, so it's not necessary to do anything in this module. Please go to load module and define your boundary condition. So for boundary condition, first we define symmetry, boundary for this section, because we consider half of our notched beam, so we consider initial and mechanical symmetry, continue, and select this line and this line by pushing shift button in your keyboard, and okay, and consider this one U1 and UR2, UR3. Okay, and okay. After that, we need to define boundary condition for this section, for this point, and just consider U2 as our constraint. So please click create and consider mechanical and displacement rotation, continue. Please select this point, done, and consider U2 and okay. And for this section we need to define load maximum 675 Newton to apply cyclic loading. So define Please click create load and select loading, mechanical, concentrated force, continue, consider this one, down, and see F1 means X direction 0 and CF2 must be 675 for example, and okay, this is our load. Okay, please consider click load manager and modify step 2 additional loading and unloading. We need to define amplitude to consider or applying cyclic loading. So after click here, edit and define amplitude. Please consider the tabular type, continue, and input this tabular zero, one, 0, 2, 1, 3, 0, 4, 1, 5, 0, and 6, 1. Okay, and define and consider amplitude 1 for the second step, and okay, and also we need to define predefined field manager, create to apply our cyclic loading in our notched beam during all second of our step. So after that, mechanical, mechanical and hardening, continue, please. Please select all of your model part and define cyclic loading, equivalent plastic strain. We consider kinematic hardening in our model, so we consider this parameter for our kinematic hardening. We have two kind of hardening: isotropic hardening and kinematic hardening. If you are interested in learning about hardening, please just do research or click search in Google and type kinematic hardening and isotropic hardening. You can get lots of information about this kind of hardening, and then continue your model and understand what you do exactly. If you have any question about kinematic hardening or isotropic hardening, please feel free and send me an email. I will be answer your question as soon as possible. So after defining parameters about kinematic hardening, please click OK, and after that you can see this kind of circle for the defining your predefined field. Okay, after this module we need to go to mesh module to define seat size and define mesh for our notched beam. Okay, so for doing this module, so first we need to define global seats. So we consider this one seat part instance and consider approximate global size 5 and okay. And for defining a seat edge or as I already explained about why we defined partition, because we need a smaller seat size in some section than other sections because of the getting accurate result for some section, like for example notched section for our beam. So for doing various seat size, we usually use seat edge. Click here and consider what line you want to define same seat size. So we consider this line and this line, this line and this line. Okay, and click by number and consider one as a number of element, and okay, so we just consider one element in this partition, and for other section, other line, we consider for example 2 and click shift simultaneously 2 and 2 and click down and consider 3 number of element here. Okay, and then consider this line and okay, and define 8 number of element here, and okay. And for this section consider this line click by size and consider 0.3 for example, and okay. And another line is for this line, this line, and okay, we consider by by number and click single as a bias. Please consider your which size, which side you need to have more smaller seat size. For example, you can see here this direction, so the seat size in here is smaller than here. So for example, we consider, for example, okay, bias ratio 5, for example, number of elements, for example 5, and bias ratio, for example 3, and apply. You can see here this size, element size, seat size is smaller than this section, and okay. And another line is, for example, this one, and this one, this one. Click down, okay, and by number, and consider, for example, number of element 10, and bias ratio, for example 15, and we need to change this direction. Select and this one, and okay, and also select this one, okay, and then okay, and you can see the seat size in this section is lower than this section. Okay, and then consider this line and this line, okay, and bias is noun, and by number and the number of element we consider 7, okay, and done. After that, please click assign mesh control and consider all of your notch beam. Select element shape must be quad, and consider a structure, sweep, and okay, sorry, consider all partition, quad, sweep, and okay, and then define assign element type. Consider all of your partition, okay, standard element library, standard geometric order quadratic, and please consider plane strain. Your element type is CPE8R, and okay. After that, please click mesh part instance and click yes, and you can see this is your mesh. And as you can see, in this section is more important for us than here, so the mesh size is smaller than here. Okay, after that please go job module and define your job. For example, job 1, continue and continue and just submit. Okay, and I use a student module, a student version of ABAQUS, so it's not possible for me to use model with 1000 nodes, so it's not possible for me to run at this moment. So I use my previous results. So I just open my model, previous model, and ODB, Nash beam, and okay, this is my model, previous model. I have already run this model and get the result. You can see here and click. You can see the result, and please click viewport, click view, ODB display option, please click mirror and consider YZ plane, and this is my whole model, Nash beam model. Please consider this and free it. You can see. Okay, and at the end of our CAE simulation, we want to draw a stress strain curve. So we just consider create XY data and ODB field out, click ODB field output, continue, and please unique node, and for example E11, and for stress we consider is one where it is one, okay, is one and save. Okay, please click element node tab and node set, and please consider test set. We define already test sets, or you can just consider we consider this node as our node set. So you can select this one and define set this node as a set in part module or assembly module as a test set, or another name you want to consider for your node. So we consider this node as our test set, so I can see the test, and then save E11 and S11 in here, and then want to plot XY data as the E11 and S11, and so click please go here, create XY data, and click operate on XY data, and click continue, and please select combine, and double click E11 and S11, and then plot. You can see this graph, a strain and a stress graph, as your hysteresis graph for your simulation. I hope you enjoyed this tutorial. If you have any question, please send me your question by email, or write message in my channel. I will answer your question as soon as possible. Please don't forget subscribe my channel, and also click a like button to increase my motivation to prepare more practical video for you. See you later.